Hi, Fiona. Can I see your face for a minute so we could talk to each other? I think it's outside of the norms, Fiona. I really think we need to be able to look at each other. I'm not saying you have to do it for the entire class, but I need you to tilt your screen when it's just you and me so we can talk.
Like now?
Right now.
Okay.
Okay. So I understand that, well, why don't you want to have your camera on?
Because I would be nervous when I see myself on the screen due to some reason of my childhood. So
Okay.
I will
But
try my best to.
okay, well, but I think it, okay. But when we're talking just you and me, I have to be able to at least see part of your face. Okay. And I appreciate this morning that you turned on your camera. I mean, I know you didn't want to, and I don't mind looking at your ceiling. That's okay. As long as you know you give me thumbs up and you can put it up so that I can see it. But everybody has to have their camera on. That's the rule. Okay? All right, you can tilt it away now. I'm going to let somebody else in. Oh, Tia, is that a background? Oh, well, it was, excuse me. No, I'm in Zoom. Take care of the dog. Sorry, everybody's home today. When I caught your background in Calc, I thought because it was so nice out, maybe you actually had like the window open, like, you know, maybe you had a sun porch or something, but now I see that nothing's moving. So, okay. Are you feeling better?
Yeah, I wish this was my window. That'd be amazing. But yeah, I'm feeling a lot better.
Good. Very good. And you didn't end up missing physics anyway because it was canceled because it was in the afternoon. So. And when is this over? This is over at 12:45. Okay. No. This is over at 1:30. Okay. There's a puppy who's eating people's socks, except that people are still wearing their socks. So there's some teeth issues, and I keep trying to say, you know, you could put her in a crate, little timeout, little, you know, reset. And both boys are like, oh, no, it's okay, we're playing. I'm like, okay, but you're gonna get hurt, and don't know what to do about that. Eva, there's a hole in your ceiling.
Yeah, it's really embarrassing.
Oh, I don't mean it that way. It's just interesting.
Yeah.
What part of your house are you in?
My basement.
Ah.
My room.
Oh, is that where your room is?
Yeah, my mom made me move downstairs.
Okay, not going to ask that. All right, so Sophie is here on Zoom. Tia is here on Zoom. Guess is absent, I'm assuming. Annabelle is here on Zoom. We don't have Lauren yet. Eva is here. Dagny is here. Fiona is here. So we'll give Lauren one more minute. And then we'll see what happens. And it turns out I was right. We were supposed to put everybody on Zoom because that's how you were here. So I didn't have to go back and redo attendance. There's a puppy 11-year-old boy wrestling match going on in my living room, so it's a little distracting. Not getting involved. Not getting involved. All right. Here's Lauren coming. Zoom, submit, yes. All right, so we got everybody. I want to reiterate what I said in Calc this morning, that it's easier with you guys because there's only 7 of you, but I still may not be able to see everybody's face when I'm sharing my screen. So it's important that if you have a question, you speak up. Don't just raise your hand because I might not necessarily see it. Just interrupt me. Excuse me, Dr. Goetz. Dr. Goetz, I have a question, and we will stop. I will try to ask and wait for longer to make sure you have time to ask your questions, but we've got to be in this partnership together here, okay? So I'm going to share my screen. I'm already recording, I think. Yep. And what I want to talk about first is not AP Calc, but AP Physics. So under forces, at the bottom down here is a new doc called Atwood's machine. Okay. An Atwood's machine is an application of Newton's second law, and it's classic. You will come across it again and again. If you retake this class when you go off to college next year or the year after, you will come across Atwood's machine. So it's kind of a self-contained thing, and we usually do a lab on it. So I'm gonna have you do this, okay? I made a video that you can watch on YouTube that takes you through the derivation of how to find the acceleration and the tension. There's a link to one of those ranking exercises where, and actually it's like right here, where you go through and it asks you questions, so you can do that. And then there is another video to kind of talk about what happens when the masses on either side get really big or really small. And then there is a lab to do. So this is a link to a document under lab experiments where you can basically run the Atwood's machine lab using a simulation, okay? An Atwood's machine is 2 masses on either side of a pulley, and you can do this, okay? It asks you to copy some data, put it into Excel, fit a line to the velocity versus time graph so that you can get acceleration, all things that we've done before. This is a real lab, but it's not a formal lab write-up. Sometimes what I do when I do labs is all I want is your data, and then I want answers to the analysis questions, okay? So you need to go through, if it's something that asks a question or like asks you down here in number 17 to draw a free body diagram, hit the space bar a bunch of times, draw your free body diagram, okay? So this is due at class time next Thursday. Okay, we will continue on. We may very well start section 6.2 tomorrow, depending on how far we get today. But I figure you have a week to do this. All right, questions about this? Okay, there will be other opportunities to ask questions about it anyway as we go. Then what we were looking at is an example of Newton's second law. So as you recall, this was example number 3. We had one object that was up here on the horizontal. It was connected by a massless, stretchless cord over a massless, frictionless pulley to another object. And then I believe we were supposed to figure out the acceleration of the system. Is that right? Yes? No? Anybody remember what we were supposed to do? Acceleration sounds right. I could look
We
it
have
up.
to find the tension in the
Oh.
connection cord.
So we were supposed to find the tension. Okay, so we were supposed to find the tension. So we set up our free body diagrams. We talked about how we are obligated to write down Newton's second law after we do that. We were working with our object that was on the incline, and remember how we talked about that we need the direction that the objects move to be positive for both objects. So our axes are a little wacky here. Positive goes to the right for the object on the horizontal, but positive goes down for the object on the incline. Okay, this is going to come back and be important in the Atwood's machine stuff too. Okay. So I think we ended with trying to figure out what the components of the gravitational force were for the box that was on the incline. And we talked about how it was a game of triangles and angles. Okay, are we all good with that then? All right, excuse me one moment. I think I've calmed the wrestling match. Okay, so, oops, what's going on over here in the chat? Oh, okay, well, when Tia, thank you for telling me, Eva, when Tia gets back, we will let her in, and I'm recording the class anyway so she can fill in what she has missed, okay? So, basically in this situation, we've got two things we don't know. Okay, we don't know what the acceleration is and we don't know what the tension is. Okay, and being that we are supposed to find the tension, we are probably going to have to somehow substitute in for the acceleration. Okay, so for box number 2, we have this equation here. So I'm going to copy that and put it on another page. And for object number 1, we have this equation that we need to work with a little more. So let's try to solve this a little bit better. Okay, so we wrote down Newton's second law. Remember that F net means we sum all the forces. So now we've written down our two forces that have components along the x-axis. So the next step is to get rid of those vector symbols and turn them into plus or minus signs. So Sophie, simply because you're on my screen, is the tension going to be in the positive direction or the negative direction?
The negative.
Right. So the tension is in the negative direction. And Lauren, what do we know about FG1X?
It's in the positive direction.
Yep, so that's going to be in the positive direction. And we talked about how we always assume that our unknown, whatever it is, in this case the acceleration, is in the positive direction. And if we're wrong, it'll pop out with a negative sign and life will go on. Okay. So if we bop to the next screen for a minute, we can see that we have a relationship here for FG1X. FG1X is going to be equal to FG1 sine 30. And we can substitute that in here. So I'm going to have negative T plus FG1 sine 30 degrees is going to be M1 times A1X. And this is the equation that I'm going to copy and put onto the same page as my equation from box 1, or box 2 rather, okay? So we've already said that the tensions are the same because a string or a rope can only have one tension. We also talked about how the accelerations have to be the same. That if the system is moving as one thing and the cord is taut, T-A-U-T, taut, then everything has the same acceleration. So I can just let A1x be equal to A2x be equal to A. So I have my F applied plus my tension, and I have a feeling here that I've messed up. Oh no, maybe not. Hang on a sec. Nope, I'm okay. And over here, I'm going to have negative T plus. I'm going to substitute M1G for my gravitational force times sine 30 is going to be M1A. And now, since what I'm looking for is the tension, I'm going to solve both of these equations for A and then set them equal to each other. So A is going to be equal to F applied plus T over M2. And over here, A is going to be equal to negative T plus M1G sine theta over M1. Okay, everybody with me? And then because it's the same acceleration, I can set those things equal to each other. So I have F applied plus T over M2 is going to be negative T plus M1G sine theta over M1. And then what do I do?
Cross multiply.
I can cross multiply because ultimately what am I trying to do here?
Solve for the tension.
Solve for the tension. Okay, so why don't you solve for the tension and I'll solve for the tension and let's see what we get. I'll let you start. And I apologize, but somewhere along the line, I changed 30 degrees back into theta, but we all know that theta is equal to that 30 degrees. So did I do my algebra right?
Can I ask why you took out an M2 on the left side when you set it equal to T?
You mean this line here?
Yeah.
Well, because what I did is I took this term and I brought it over to the other side so that I had M1T plus M2T, and I was able to factor out a T.
I forgot about the other T. Thank you.
Cool. So I'm fairly confident that my algebra here agrees with my algebra from the past. So if you want to substitute the values in and see what you get for T, that would be a great next step. Did she go upstairs? Oh, she's here. She can be here. Actually, Mira, come here. Mira, come here. Come here, girl. Oh, come up here for a minute. Eva.
Oh my gosh.
Eva wanted to know if
So
Mira could photobomb when we went to remote. So here we are. And here's the pandemic puppy. This is sweet girl. Okay, go back and play with your brother. Yep. Oh. Okay. Don't eat the cord. Share screen. Okay. All right, so what do we got for T?
I got negative 4.25 newtons.
It should not be negative. Remember, everything that you're plugging in should be positive. So like G, for instance, the G that we're talking about here, whoops, is a magnitude. So G should be 9.8 meters per second squared. No positives or negatives.
Okay, that's why.
Okay. Because we've already taken, Leo, go get the dog. She's on the chair over there. Because we've already taken that negative sign into account when we got rid of the arrow over the FG1 or FG2. Okay. So anybody have a different answer?
So it is 3.1 newtons.
So Fiona says 3.1 newtons. Did anybody else get 3.1 newtons?
did.
Yes.
Lauren did. Annabelle, you didn't. What'd you get, Annabelle?
I also got 4.3 newtons.
Did you make G negative?
I did, but then I took out the negative. So I got negative 4.3 at first, the same as Lauren, and then
And then what did you get when you took that negative sign out?
hold on. Let me just double check, sorry. I'm doing something different now. I think I did something wrong.
Okay, well, try it again now if you have time later on your own, and make sure that you're putting parentheses around the right stuff. Make sure you're in degree mode, not radian mode, is another biggie. Okay, but the answer is in fact 3.1 newtons. Okay. So somebody read us part B. What does part B say?
Part B says, what is the largest value that the magnitude of F can have without the connection cord becoming slack?
Okay. So if the connecting cord becomes slack, okay, and remember that instead of being straight, it goes like this. What do you think happens to the tension when it goes slack?
Tension becomes 0.
Yeah, the tension is going to become 0. Okay, and that means that the two objects can now kind of move independently. There's nothing that's connecting them. So if we go back and we look at the equations that we had, so I'm just going to go back again. Let's see, I can start from here. Okay, so I had these two equations. Paste. Okay, so I have these two equations that were the result of my free body diagrams. Okay, so if I let t go to 0 here, then my applied force is going to be whatever is causing the acceleration. Okay. And if my tension force goes to 0 here, then I can say that this FG1 sine 30 degrees is going to give me M1A. So that means that I kind of know what my acceleration is going to be if the cord goes slack. Okay. So this is going to be M1G sine 30 degrees is going to be M1A. My M1s cancel. And what's this acceleration going to be?
.9 meters per second squared.
Okay, so I have 4.9 meters per second squared, and then this can go up here, and I can say that that applied force is going to be M2, which I think that's the 3.0 Newton, 3.0 kilograms times the 4.9 meters per second squared. And what's that applied force going to be?
14.7 newtons.
And I think we have 2 sig figs, so let's call it 15. Okay. And so what I'm really talking about in this situation is kind of that if I go, I can get as close as I want to 15 newtons with my extra push. But if I get to 15 newtons, then the tension is going to be slack. Okay, and there will be the rope will be slack and there will be no tension anymore. So this is my upper limit. I can get as close as I want to it, but once my applied force hits 15 newtons, the cord goes slack and my system isn't behaving like a single entity anymore. Okay, make sense? We good? Yes, try to cycle through everybody here. All right. Okay, some thumbs up. I love the thumbs up. All right, so now we want to talk about Newton's third law. Which you read about, okay? So we want to back up, or I like to back up, and talk about the normal force again. Okay, so if I have some kind of table or whatever, and I have a book that's sitting on the table, then the normal force is that force that keeps the book from falling through the table or pushing through the table. And I might call that the force of the table on the book. But just by saying that the normal force is the force that keeps my book from falling through the table, that implies that there's a force of the book on the table that has to be balanced out somehow or counteracted on by the table. So the force of the table on the book and the force of the book on the table are what we call a third law pair. And Newton's third law tells us that when two bodies interact, the forces from the body on each other, from the bodies on each other, are equal in magnitude and opposite in direction. Whoa, things are flying. I probably need something better, but you can see this, okay? So if I have, this is my Kindle and my lotion bottle, okay? The lotion bottle is pushing down on my Kindle, and my Kindle is pushing back up on the lotion bottle. That makes a third law pair. And as we've talked about a bunch of times, there's also kind of a language thing that goes with it. So the force of the bottle on the book is equal in magnitude and opposite in direction to the force of the book on the bottle. Okay, so the words change places. The force of the table on the book is equal in magnitude and opposite in direction to the force of the book on the table. Okay, so object 1 and object 2 flip positions when we talk about those forces. Okay. Another way of saying Newton's third law, which is kind of the way it's said more regularly, is for every action there is an equal in magnitude and opposite in direction reaction. So sometimes we call third law pairs action-reaction pairs. Okay. Something really important to remember is only one, that's horrible, let's write that again because this is really important. Only one force of a third law pair goes in a free body diagram. Okay. Again, to go back to my bottle on my book example, okay, if I'm drawing the free body diagram for the bottle, then I'm going to have the force from the book. It's going to push up. If I'm drawing the free body diagram for the book, I'm going to have the force from the bottle pushing down. But remember, when I draw a free body diagram, I'm drawing the forces that act on the object. So if I go back up here again, this force goes in a free body diagram for the book because it's acting on the book. This force goes in a free body diagram for the table because it's the force on the table. Okay, does everybody understand what we're talking about? Yes? Annabelle's giving me a thumbs up.
Dr. Guess,
Yes, Lauren.
is this like the normal force for both?
Sometimes we think about it that way, yes.
Okay.
Mm-hmm.
Okay, thank you.
As long as you don't, that's why I don't like to think of the normal force as the support force. Because when I'm talking about the book on the table or the bottle on the box or the bottle on the book, okay, they are both exerting normal forces on each other, but it's not like the bottle is supporting the book. Okay, it's much easier to see that the book is supporting the bottle because it's holding it up. But yes, that is a normal force too. Anytime I have two objects that are pushing against each other, there's a normal force that one exerts on the other. So whether it's the book pushing up on the bottle or the bottle pushing down on the book, those are, yes, both normal forces.
Okay, thank you.
Okay. All right, so let's see what I want to do here. All right. Does everybody have written down here what they need to write down here? Yes? Okay. Then I think what I'm going to do is the next step is the next thing in my notes is I have a couple problems I want to do. So I think what we'll do is we will save those problems for tomorrow where we have class plus flex. And they're kind of lengthy problems with a lot of important things to say. And I don't want to start in the middle. 6 minutes is not going to get us very far in. So in a minute, I'm going to end class. We will do the problems that go with Newton's third law tomorrow, which will look a lot like the problems we did for Newton's second law. And then you don't have to read 6.2 for tomorrow. You can read it for Monday. And I will change what's on the portal. 6.1 is basically a bunch of examples applying Newton's laws. You can read it if you want. There's nothing bad in there. There's nothing I disagree with, but I'm going to do examples that will give you that same information. So either we've already done those examples or we're going to do examples. So I'm not requiring you to read 6.1. We're going to start with 6.2, which is friction. The reading guide is already up there if you want to get a head start, but we'll move that to Monday. and tomorrow we'll just finish chapter 5. Okay, makes sense? Okay, so does anybody have homework questions that they want to talk about? I know I've already met with a couple people. I know Dagny has some homework questions. I don't know if anybody else has homework questions. Lauren, what else do you have?
I just wanted to confirm for when you're looking at an object and just the forces that are being applied to that object, you would focus on when you take F net, that would just be the forces being acted upon the object that are given. Like when
Which problem are you talking about? Let's talk about what specific problem is causing you to pause here.
For number one, and number two, both of those I did not include the FG or FN.
Okay. Yes. Now the thing is, and the reason why that's okay is because in problem 1, it says the forces are acting horizontally. So again, what's happening in problem 1 is you're looking down on the object. So for homework number 1, here's my box, and there's a force that goes west and a force that kind of goes that way, I think.
Yeah.
Is that approximately right? Okay. So, but what's happening is the gravitational force is coming, nope, that's not true. I take that back. The gravitational force now is going into the page. Okay, because I can think about this box as sitting on my table. Okay, and basically you have a string that you're pulling one way and I have a string that I'm pulling another, but the box is moving around on the surface of the table. So the gravitational force is going into the page, the normal force is coming out of the page. Okay, and that's kind of how we do it. When we have forces going into the page, we make an X. When we have forces coming out of the page, it's a dot, because you're kind of seeing the point of the arrow or the back of the arrow, which is the cross. Okay, so the reason in number 1 why you can ignore the normal force and the gravitational force is because they're perpendicular to the direction that the object is moving around. So they're kind of like in the Z direction, and because the box isn't popping up and down, there's no acceleration in that direction. So those forces are in equilibrium with each other and they cancel each other out. Okay, and then in number 2, it's a similar thing, except in number 2, it actually tells you that it's an overhead view, but it's the same thing. I'm looking down. I know I have a force going off in positive X. I have some other force going in another direction that I don't know, and I know by the acceleration which direction my block is moving. But again, the normal force is coming out of that picture, and the gravitational force is going into that picture because I'm looking down at a box that's on the table. Okay, so those forces really are there. It's just that they're canceling each other out because of the way the problem is set up.
Okay.
So you probably did it right. You probably did it right. It's just that you need to know why you did it right.
Right, exactly.
Okay.
Thank you so much.
All right. Are there other questions? Dagny, does that help you? No? Okay, that's cool. Dagny, do you want to ask your question and maybe other people will benefit from it?
I mean, I was just really confused on 3, so.
Okay, well then let's talk about number 3 for a minute. Okay, it is still technically class time. Okay, so what does this sound like? I've got a car, it's got an initial speed, it stops in a certain distance, Dagny. What does that sound like to you?
Projectile motion?
Even simpler than projectile motion, because the car's not shooting through the air, it's moving in one direction.
Like linear motion?
Yeah,
Dimension.
It's linear motion in one dimension. Okay. So there's a force, it says here, that stops the car, a constant force. What do forces cause? Dagny.
Acceleration.
Yeah, forces cause acceleration. Okay, so your first, okay, so forces cause acceleration. And what's that relationship between force and acceleration?
Like when.
It's an equation.
Oh.
What equation has a force and acceleration in it?
F net equals ma.
Right. And the only force that's acting in this horizontal direction of motion is the brakes.
Right.
Okay. So really your F net is the F of the brakes is equal to ma. So if you could figure out the acceleration, you could figure out what the force is, right?
Yeah.
Okay. And part B, the time necessary, that's just a chapter 2 problem.
Okay.
Right? Because you know you have an initial speed or velocity. It comes to a stop, so you have a final velocity. You know what that distance is, so you know x0 and x. So you could really find a and t, right?
Yeah.
So that gives you a and b.
Right.
Okay. C and D is now I'm going to change the initial speed, but it says the car experiences the same force during braking. That means F stays the same. And if F stays the same, what else stays the same? Because the mass of the car is going to be the same.
Would the acceleration stay the same?
Yeah, it's going to be the same acceleration. So kind of C and D is asking you to solve the problem again, but now you have a different initial velocity.
Okay.
Does that help?
Yeah. And then this is like an unrelated question,
Go for it.
but whenever you have something with like, so like mass is measured in kilograms, is
Yes.
weight also measured in kilograms, or is weight in newtons?
Weight is in newtons because weight is a force.
Okay, so then whenever you have kilograms, you don't have to use, like you don't, okay, that was my, okay.
So here you're given a weight. You're going
Right.
to have to convert that into kilograms
Okay.
for F equals ma.
Okay.
Okay. Any other homework questions? So I won't be grading the homework until later tonight. So if you need a couple, if something that we have discussed here makes you go, oh, I need to redo that problem, take the time and redo the problem. Okay, because I won't be grading the homework until tonight, at least. Okay. All right, anything else? Okay, then you guys are free for the afternoon. Dagny, do you have calc questions too? Okay, so you hang around. And everybody else, I will see you tomorrow in Zoom. Same bat time, same bat channel.
Okay.
All right, what's
So
up, Dagny?
all my physics questions are answered, which is
Good.
a good thing. I'll just try and redo that problem. Okay, so for calc, I know everything has to be in radians.
Yeah.
So this is like a really basic, I'm gonna share my screen because I think that would be easier.
Can you, I don't know if you can.
No, I can't.
Okay, but what I can do is share my screen. And then this is calc, I don't know what's going on here. Calc homework, right?
Yeah, it's 3.5, 3.6, and 3.8.
Okay, so it's in your OneNote notebook.
Mm-hmm.
So, there we go. Okay, so what do you want to show me? Which one?
B of 2.
Okay, so let's see. I happen to have the answer key right here. Do you know what pi over 4 is in degrees?
45.
Right. So what's the cosine of 45 degrees?
Would it be 1 and then you multiply?
The tangent of 45 degrees is 1.
Oh, right. So it's the pi over 2 over, oh no, what did I just do? Hang on.
You know, you can really just pop it into your calculator. It's okay.
Oh, okay.
Just pop it in. And if you are in radian mode, if you take 2 cosine pi over 4 minus 3 sine pi over 4, you should get a number.
Okay, I just wanted to make sure that was okay. Like,
Yeah.
like putting it into your, like if that would give you the right answer, because I know sometimes the calculator does weird things. Okay. So
Right, but this time, because pi over 4 is less than pi over 2, the reference angle is the angle we're talking about.
Okay.
So I applaud you for thinking about that, but this time it's okay because
Okay.
the reference angle is the same thing as the angle we're actually dealing with.
Okay, that makes sense.
Okay?
So then that answers, I think, everything. Yeah, because like then the speed would just be the absolute value of the velocity.
Yep.
All right, so then number 4.
Yep.
I just feel like there's a lot going on here, and I don't know if I did chain rule right.
Let's see. So you get 2x. I think I can draw on here. You should have, there should be an exponent here, right?
Right. I always forget that exponent. Okay. So then it would just be negative 1/2.
Right, which it looks like you actually took care of everywhere except for right there.
Right.
Like I think you just didn't copy it over or something, but yeah, you need an exponent there. So I'm actually gonna, I don't know if that did the right thing or not. I tried to undo it. Yep, so you can put, but that's the only thing that seems to be off.
And then when can you
Oh, hang on. Just let me see for a sec. I feel you need to check your algebra. Okay?
Okay.
Because like I agree. I do. I agree with this line here. But then you did, I have no idea what you did to get to the next line, but you messed something up.
Okay.
So that line is okay. And then when you tried to combine some things, it went wacky.
Right.
So
would the 2x times the like, because in the line that you agree with, like, can you combine the 1/2 secant x negative to the exponent of negative 1/2 with the secant squared x tan squared x? I didn't think you could, right?
no.
Okay.
No, and actually this is, you look up what the derivative of secant is, because
Okay.
I'm pretty sure it's secant x tan x, not secant squared x tangent squared x. So actually, I don't totally agree with that line because I think you wrote down the wrong. I think you wrote down the wrong derivative.
Okay.
Okay.
Yeah, I'll check that.
I mean, what you can do is you can cancel the 2 and the 1/2.
Yeah, which I did.
No, you didn't. You
did.
might have thought you did, but you didn't. And you ended up with an extra x, and I don't know where that came from. I don't know.
Oh, I put 2x instead of 2. That's why. No, I
Okay.
didn't.
I don't know what you did,
I don't
but
know what I did. I'll check.
yeah, but the expression in the box is wrong.
Okay.
Okay.
All right. And then for 5D,
Yep.
so would you have to do, I did something weird, I don't know if that's right.
Okay.
But
this is wrong.
Okay.
You can't do that.
Okay. Great. So then how would I guess I just didn't know how to solve that.
Well, again, how do I want to put it? Basically, you're just using chain rule.
So is your inside function the x plus gx?
Yes.
Oh, okay. I thought that you would have to do like an inside of an inside function.
No. So, I mean, let's see. Okay. this is wrong because you did your, because what's this equal to?
Oh, just 1,
And what's this equal to?
5,
And you're going to
Oh,
add them, right?
6. Yeah.
Okay. So that's okay. So up here, for instance, and this is wrong too. So let's go through, let's look at number C.
Okay.
Okay. So you're going to use the chain rule. What's your outside function?
F of G
F.
of
Let's
X.
just call it F.
Okay.
Okay. What's your inside function?
G of X.
G of X. Okay. So when you use chain rule, you take the derivative of the outside function at the inside function times the derivative of the inside function.
Right.
Okay. And then for C, it's all 0. So you're going to take F prime of G of 0 times G prime of 0.
Right.
Okay. What's G of 0 from
1.
the table?
And then G prime of 0 is 1/3.
Okay. All right. So but now what's F prime of 1?
Oh, 3.
No.
Oh, sorry, F prime of 1 is negative 1/3.
Okay. And then you told me G prime of 0 was 1/3.
Mm-hmm.
Okay. So use this as a model for doing part D. It's going to be a little more
Okay.
complicated, but use that as a model.
Right. Okay. And then just going down, I think the last one I had was, I had no idea if I did this right at all.
No, you didn't erase it.
I didn't.
Just get rid of
think
it.
so,
Just erase
'cause
it.
it seemed not right when I wrote it.
Well, and you didn't prove what you were supposed to prove.
Yeah, I didn't see how you could prove that, I guess.
Erase it. Did you erase it?
I did.
Okay. All right. So your first sentence up here. So the velocity is inversely proportional to radical x, or radical s, rather. Okay. So what does that mean? Inversely proportional.
So doesn't it mean that like when the velocity goes up, or like if s is increasing, then the velocity is decreasing?
Right. Is that what happened when you wrote v of t was equal to radical s?
No, that would just be proportional.
So what do you have to do to make it inversely proportional?
Would you do the could you do the inverse?
What do you mean by inverse?
Well, like, you know how we were talking about today, you could do like, I don't know what it's called, but like implicit, like could you use the inverse and
No, you
like,
don't want to
find
do
the
it.
derivative?
It's not that kind of an inverse. It just,
Okay.
here inverse means opposite.
Okay.
So how do I write it? V
So
of
would it just
t,
be s squared
no,
negative?
no. If, think about it this way. Let's just talk about y and x for a minute.
Okay.
Okay, so if I want x, if I want it so that when x gets big, y gets small, how do I write that equation? Y equals what?
If x gets big and y gets
Then
small.
x getting big means y gets small. Do I write it this way? What does this mean? If x gets big, what happens to y?
Y gets big too.
Right. So if what I want is when x gets big, y gets small, what do I do? How, not
Y?
negative, because
Oh.
positive and negative don't mean big and small,
Right.
they just mean direction.
You could do. Oh no, you can't do x squared because that would.
No, that would make y get big.
I have no idea.
How about 1 over x?
But then, wouldn't x still be small?
No. If x equals 10, what does y equal?
1/10. Yeah.
Okay. If x equals 100, y equals 100th, which is even smaller.
Yeah.
Okay, so how are you going to write the velocity is inversely proportional to radical x?
1 over radical s.
Okay, so so go ahead, but what I would actually do is write, let's write it this way, v of t is equal to k over radical s.
Then would k just be the constant?
Yes, k is a constant of proportionality. It doesn't matter, but there's nothing in here that says that v is equal to 1 over radical s. It just says that v behaves like 1 over radical s, but we can put that constant of proportionality in there.
Okay.
Okay, so just leave it as that. Okay, so now, hang on, I'm trying to sync up here again so I can see what you wrote. So now what you want to do is you want to make an expression about the acceleration. So what is acceleration always equal to?
The derivative of the velocity.
The time derivative of the velocity. So write a equals dv dt.
It's written. It just
Okay,
doesn't
I
show
believe you. It'll take a bit. Okay. So that means you need to take the derivative of k over radical s. But the
Right.
problem is that s isn't a t. Okay, v is not an explicit function of t. It's an implicit function of t because s is really a function of t.
So is it kind of like when we do y for like you have to do every time you say y because y is like
Kind of.
okay.
And really, sorry, I gotta shift positions. And really, it's not just that. It's that it's chain rule is what it really is. Okay, so I'd go back to your v of t expression and say that that's going to be equal to k times s to the negative 1/2, just because it's easier to take the derivative. Okay, and then what you want to do is take the derivative.
Right. So then it would be equal to k, and then because k is just a constant, you could just
leave it out front.
K. Right.
Yep,
Okay.
just leave it out front.
Negative 1/2 s.
To the negative 3/2, right?
Yeah.
But because s isn't a t, you have to write ds dt after it.
Because s is a function of t or t is a function?
Yes, because
Okay.
s is a function of t. Because what is s? I meant to ask you that a couple minutes ago. What does s stand for? I mean, what does s represent?
Like the distance from the Earth's center.
Right, and that's going to change with time because the whole point is that they're using the wrong word, but the whole point is that the meteor is rushing towards the Earth. It's moving towards the Earth. Okay?
Yeah.
All right, so what is ds dt? What does that represent?
The derivative of just s. Well,
right.
Yeah.
But what is it? When you take the derivative of the position with respect to time, what is that? That is something. That's another quantity that we talk about.
that would just be velocity, position with respect.
It would just be velocity. And you have an expression for velocity. So you can substitute back in for dsdt.
And you would just substitute k over radical s.
Yep. And if you do that and you combine all your exponents and put them in the right spot, you should get some function of k, I don't know, I think it's k squared, over s squared.
Okay. Okay, so then when I'm combining, so I would combine both of those and then get okay, this makes sense then. And then I would just combine it and go from there.
Yeah, just combine all your exponents. Put all your whatever. You know how to combine
Yeah.
exponents.
Yeah. Okay, that is all.
Okay, great.
Yeah. Yeah, thank you so much.
No problem.
Bye.
Bye. See you tomorrow.